This section is about triple integrals, and just like we did for single integrals and double integrals, we're going to build into it. Everything we've done with double integrals, we're now going to do with a triple integral as well. And we're going to start with looking at a rectangle. We're going to look at the triple integral over a rectangle because that's the easiest place to start and build up from there. So if you were to take this rectangle, divide it into boxes, and pull a box out, you can do a triple Riemann sum, which we then can write as a triple integral. So the triple integral of the box is the triple sum over the box. Again, this triple integral always exists if f is continuous. So you can pick any point in the box and you can write the triple integral. But we have Fubini's theorem for triple integrals down here. And if f is continuous on the rectangular box B, where x is from A to B, y is from C to D, and z is from R to S, then we have the triple integral as shown below. And so we're going to start with finding the triple integral over a box using Fubini's theorem. So all of that to say, right, focus on this Fubini's theorem. It's not always going to be that nice and simple, and I don't know that you really need to write it down. But Fubini's theorem is the integral that says that we can integrate over your triple integral. So this problem says to evaluate the triple integral xyz squared with respect to the volume, where B is the rectangular box given by B is equal to xyz such that x is between 0 and 1, y is between -1 and 2, and z is between 0 and 3. So what we're going to do is we're going to write the triple integral over B, and it's xyz squared with respect to the volume. And then we're going to set this up to be a triple integral. So I'm going to leave some space for the bounds. And we have xyz squared. And let's do it in order, dx, dy, dz. So my x bounds, my inner one, are 0 to 1. The y is -1 to 2. And the z bounds are 0 to 3. And then we're going to do like we did earlier and work from the inside out. So let's start with x. So we're going to bring down the other two integral symbols. When we integrate x, we get 1/2 x squared. And I'm going to say here x equals 0 to x equals 1 to help me focus on which variable I'm using. So we're going to bring down the rest of the integral symbols. -1 to 2. That should be a 2 there. And when we plug in 1, we get 1/2. I'm going to say 1/2 times 1 minus 0, yz squared, dy dz. So the integral from 0 to 3, -1 to 2. And then we have 1/2 yz squared. And we're going to integrate with respect to y and then with respect to z. So now let's pick up with our y. I'm going to switch colors. We have 0 to 3. And we have 1/2, and then we have 1/2 when we integrate the y, so I'm going to call it 1/4 y squared, z squared, and this is y equals -1 to y equals 2, and then we're going to integrate with respect to z afterwards. So we have the integral from 0 to 3, we have 1/4, 2 squared is 4, minus 1 squared is 1, z squared with respect to z. So we have the integral from 0 to 3, 4 minus 1 is 3, so we have 3/4 z squared with respect to z. So now we can integrate with respect to z. So when we do that, we get 3 over z squared becomes z to the third, and 3 times 4 is 12, and our bounds are 0 to 3. Let's reduce that to be 1/4 z to the third from 0 to 3. So this means we have 1/4 27 minus 0, which is 27 over 4. So our triple integral over this box, the rectangular box, gives us the value of 27 over 4. When we look at triple integrals over a general region, we're going to start off pretty much the same as we did for double integrals. We're going to enclose E, our bounded region, in a box of the same type of as an equation, and then we're going to define a region F so it agrees with E. So let's look at a couple of pictures here. So here we have several pictures happening. The first one is a type 1 solid region. So here we're talking about finding the volume of the solid E. So if you look at this first figure, figure 2, you see the volume for the solid E, and it gets mapped to a region on the xy plane like we've been doing with our integrals so far. If you look at figure 3, you have a type 1 solid region. This is the second picture here, where the projection is a type 1 plane region. Remember that the type 1 plane region is when your x, you have boundaries for x, like 2 to 4, and then your y was between two equations. That was a type 1 region. And then figure 4 is a type 1 region with a type 2 projection. So down here, this means our x is between bounds. So let's talk about what these look like in triple integrals. So when we look at the first two, let's say figure 3, we have the triple integral here, and we're going to say that we can consider the double integral we had before, but then we have another integral, and it says the integral from u1 to u2. This is our u1 in terms of xy, it's an equation, to u2 in terms of xy, and our equation is f of xyz. And then we have, with respect to z, and then we have dA. So technically, this is the one we're putting in the middle. Is in order to find it, we're starting with our integral with respect to z. This is for figure 3 here. Notice that z is between u1 and u2. I underlined them backwards, but hopefully you see that happening there. So this goes with figure 3. Let's go one step further, and let's say we have 3 integrals. And if you look at our integrals here, if we look carefully, we can fill this out. So I'm going to start with the fact that let's start with x as our first one, because notice x is bounded by a and b. X is between a and b, so this is a to b. And then if we look at the y's, y goes from g1 to g2. So I'm going to say g1 of x, g2 of x. And then we have the integral from u1 of xy to u2 of xy. And we're taking the integral of the function in terms of xy and z. And we have dz and then dx and then dy and then dx. So this would be our figure 3, where we have a type 1 solid and a type 1 region. And the integral won't be that difficult at this point. It's just setting it up. So let's look at the figure 4. It says a type 1 solid region with a type 2 projection. So if you look at this, we're going to start off the same. Notice that your y value is c to d. That's the difference between your type 1 and type 2 projections. So let's start with c to d for y. So that means I'm going to have dy out here as last. And then our x's go from h1 to h2. So we have h1 of y to h2 of y. And then we have u1 in terms of xy to u2 of xy. And we have our function of xyz. And we're doing dz first, and then dx, and lastly dy. So let's look at one of these problems and how it looks before we move into other types. These are all type 1 solids. A type 1 solid is a three-dimensional solid that is continuous, and it lies between the graphs of two continuous functions. So the definition is that u2 of x and u1 of x have to be continuous functions. Okay, so let's look at one of these. Evaluate the triple integral over e of z in respect to dv, where e is the solid in the first octant, bounded by the surface z equals 12xy, and the planes y equals x and x equals 1. When you do a triple integral, you need to think about two graphs, so to speak, or sketches. So let's start with the one of z equals 12xy. Now, feel free to look that up in Desmos or in a graphing utility or sketch it out. So let me put that here for us. So here we have a really pretty graph. The bottom sits on the z equals 0, so it sits on the xy plane. Look at that pretty triangle it makes. And the top is bounded by z equals 12xy. We also need to look at what this maps to in the xy plane. So if you look at the fact that we have 12xy is equal to z. That's our main equation, but it's bounded by the planes y equals x. That's this line right here. Y equals x and x equals 1. And x equals 1. So this is our boundary in the xy plane. You can see it down below down there. And as it comes up, it affects that 3D figure. So we're going to say that our bounds for x are 0 to 1. I really like this notation so much better than the other, but we're going to have to use the other, so I'll move into it in a minute. And then our bound for y would be 0 to x. So we can say that our domain of E, so E is equal to the points x, y, z, such that x is between 0 and 1, and y is between 0 and x, and z is between 0 and 12xy. You can see that when x is 0 and y is 0, then z is 0. So we're going to build our triple integral. I'm going to start with the outside being x because the bounds are 0 to 1. And then the next integral will be y from 0 to x because it has an x in the integrand. And then the z will be 0 to 12xy. And if you go back up here, we're evaluating the triple integral of z over the volume. So z goes here, and then we're going to work from z, and then we have y, and then we have x. So now that we have set up, we're going to do this first integral here. So we have the integral from 0 to 1, the integral from 0 to x. We integrate z, we get 1/2 z squared, and we're going to go from z equals 0 to z equals 12xy. Then we will integrate with respect to y and then with respect to x. So now when we integrate, let's plug in those values for z. We have 1/2 times 144, x squared y squared minus 0. And then we're going to integrate with respect to y and then with respect to x. Bring all that down. Half of 144 is 72, x squared y squared. We're going to integrate now with respect to y. So let's move this up, and as we integrate with respect to y, we're going to bring the outside down. So we're going to say 72 x squared times 1/3 y to the third, and we're going to go from y equals 0 to y equals x, and then we'll integrate with respect to x lastly. So we have 0 to 1, 72 x squared. Well, 1/3 of 72, let's go ahead and handle that. 1/3 of 72 is 24. So let's say 24 x squared. And then we have y to the third, so that's x to the third minus 0. We'll integrate lastly with respect to x. So we have 24 x to the fifth with respect to x is our next integral. Now when we integrate with respect to x, we get 24 times 1/6 x to the sixth. The bounds are 0 to 1. So we have 4x to the sixth, and the bounds are 0 to 1. So we have 4 minus 0 is 4. So that is the value of the triple integral of the volume in the first quadrant. So it's not too bad, it's just a little tedious, and we know that to be true. This picture down here shows how the solid of E is swept out by the iterated triple integral when you integrate first with respect to z, and then with respect to y, and lastly with respect to x. So it's kind of cool to look at, but not important to be able to draw. So here we have pictures of a type 2 and a type 3 region. Remember, in a type 1 region, your region is z is between u1 and u2. So in a type 1, z is between u1 and u2. And in the type 2 region, x is between u1 and u2. I wrote that weird. And in a type 3 region, y is between u1 and u2. So your main function that you're given is in terms of x, y, or z. I don't know that it's important that you memorize. I've never felt it's important that you memorize what type it is, just that you can build the equation. So on the type 2, you would have a double equation, and then like we wrote the other one, it would be u1 to u2 in terms of yz And you would have your function of x, y, z here. And then you would have dx. And then you would do dA in terms of y and z accordingly. And in the second one, we'd have our double integral, and then our triple integral would be from u1 in terms of xz to u2 in terms of xz of f of xyz dy, and then you would have the area, and you would use your x and your z accordingly. So I've never felt it important to memorize type 1, type 2, type 3. Just read what you're given and look at the fact that in this type 2, we're taking it to the, you have your x equations here, so we're taking it to the yz plane. And on your type 3, you have your y equations, so we're taking our region to the xz plane. So just pay attention to what you're given and think about what it is. That's what makes calculus hard. It's not the same every time. You have to stop and think about what's going on. So in this problem, we're going to evaluate the triple integral of x squared plus z squared in terms of the volume, where E is the region bounded by the paraboloid y equals x squared plus z squared, and the plane y equals 4. Now, what's important for you to catch here is if you were looking at types, here your equation is in terms of y, so this would be a type 3 region, but I'm not really worried about that. Let's talk about this paraboloid. So if we sketch out our paraboloid, it goes over the x-axis, so we have a parabola of x squared plus, a paraboloid of x squared plus z squared, and then we have the plane y equals 4. Now, since this is in terms of y, and we're using that, we need to consider the xz plane. So that means it draws out over to here. It draws a circle over here with the radius of 2 when you push everything flat to the axis. So when we consider our xz plane, what we have is we have a circle with a radius of 2, the diameter of 4, the radius of 2. So we can say that x squared plus z squared equals 4, and that's how we get our center with the circle of 0, 0, and the radius is 2. Now remember, this is also polar. The r squared equals x squared plus z squared. That's going to be helpful for us. It always is. And this equals 4, so we can say that r equals 2. So all of that pulls this into play. So our region is this region here inside the circle, which is the xz plane. And we have a circle with a radius of 2. So let's move forward with this. And we have the double integral, the triple integral, let's say over the region E. Let's cheat and do what they're doing. And we have the square root of x squared plus z squared with respect to the volume. Now, let's pull this in just a little bit. So let's use the notation on the previous screen and say the double integral, and then we're going to look at the inside integral. Now, we're working in terms of y, so we have two equations, the paraboloid and the plane, y equals 4. So that means our bounds go from the paraboloid x squared plus z squared to the plane 4, and our equation is x squared plus z squared, and we're integrating with respect to y. And then we have the integration with respect to the area, where we're going to use x and z. Now we could go ahead and figure bounds and all that, but we're going to need to switch to polar eventually. But let's go ahead and look at this integral here. So when we integrate this, we get the square root of x squared plus z squared times y, and then our bounds are y equals x squared plus z squared to y equals 4. And when we're finished, then we have to still keep going. So we have the double integral out here, and the square root of x squared plus z squared. And here we have 4 minus x squared plus z squared. So it becomes minus x squared. Let's put parentheses and say plus z squared, because we are going to switch to polar, but now I have too many parentheses, so let's make this one a bracket. And then here we still have dA. So if we were to put it in terms of x and z, there's a whole lot of stuff going on. So let's change this to polar and we're using the xz plane. So we're going to keep the x is equal to r cosine theta. And instead of y equals r sine theta, we're going to say z equals r sine theta. It's easier to switch to polar in two variables, so that's why we went ahead and integrated y to do this. And then we can continue with the problem, and it's not too bad. So we know that x and z are equal to these values, but let's go ahead and say that r squared equals x squared plus z squared in this case. So we're going to have the double integral here, and we have the square root of r squared, parentheses 4 minus r squared. That's why I left that the way it was. And in place of dA, well, let's keep dA for just a minute, but in place of dA, we're going to say r dr d theta. So let's build our double integral here. The square root of r squared is r. We have 4 minus r squared. And then when we switch to polar, we have r dr d theta. Our bounds for theta are 0 to 2 pi, which is nice and easy. And our bounds for r are 0 to 2. Go back up to that circle we had at the beginning, and the radius is 2. So the bounds for r are 0 to 2. So what we really have here is we have the bounds from 0 to 2, pi, and then the bounds from 0 to 2. And we have an r at the front and an r at the back. So let's distribute those and say 4r squared minus r to the 4th dr d theta. That's not too bad of an integral. We have the integral from 0 to 2 pi. When we integrate 4r squared, we get 4 thirds r to the 3rd minus 1/5 r to the 5th from 0 to 2. I think I'm going to say r equals 0 to r equals 2. It's all r, but it doesn't hurt to be a little more specific at times. So we're going to keep the integral in terms of theta. And when we plug in 2, we get 2 to the 3rd is 8 times 4 is 32 over 3 minus 32 over 5. It's a very common fraction for us in calculus. Minus 0 plus 0, so I'm just going to leave those off. D theta. Now notice that we are in terms of theta, and there is no theta, so this is a constant. But let's go ahead and get common denominators, and I'm going to do it on my screen, not in my head, because I will mess it up. If I multiply the second one by 3, I get 96. If I multiply the first one by 5, I get 160. So I have the integral from 0 to 2 pi, and 160 minus 96 is 64 over 15 d theta. So when we integrate with respect to theta, we get 64 over 15 theta from 0 to 2 pi. So this means we have 64 over 15 times 2 pi minus 0, which gives us 128 pi over 15. And that is our answer to the triple integral and the volume that we're finding. Before we move on, let's look at one more of these. So this problem says to express the triple integral over dv as an iterated integral for the function in the solid E, and then evaluate it. So when we look at this triple integral, let's start with the fact that we have the triple integral over E of dv. And they tell us what I didn't put in the picture is f of x, y, z equals x. So what we're really doing is the triple integral over the region E of x, and with respect to the volume. Now if we look at this, it sits on the xy plane, and since it sits on the xy plane, this means that z equals 0 is the bottom of the base, and it sits against this plane over here in the backdrop, the xz plane. So that means over here we have y equals 0. So when we look at these bounds, we know that y is between 0 and, let's solve this one for y. So y equals 2 minus z. So y is between 0 and 2 minus z. And then z is between 0 and 1 minus x squared. So that means since we have equations for the boundaries of both of those, that means our x needs to be values, not equations. So in order to find what x is in between, let's go ahead and set, if we look at these equations, we have an x in this equation over here, the z equation. So if we let z equal 0, we get 1 minus x squared. 0 equals 1 minus x squared. So x squared equals 1, so x equals plus and minus 1. So our bounds for x are x is between plus and minus 1. So let's start with our triple integral, and I'm going to start with x. X is going to go from negative 1 to positive 1. Now, it doesn't really matter whether you do y or z first. Z has a squared in it. Let's go zyx, just why not? So I'm going to put y here. So y is from 0 to 2 minus z. And then, oh, you can't do it that way because you've got a z in here, so z has to happen before y. So let's scratch this and try again. We're going to say negative 1 to 1 for x. And then z has the x, which leads into the last integral, so 1 minus x squared. And then y is 0 to 2 minus z. See the z here? It has to happen before you integrate with respect to z. So our function here is x, and then we're integrating with respect to y, and then with respect to z, and then with respect to x. So let's go ahead and integrate with respect to y. So we're going to say the integral from negative 1 to 1, the integral from 0 to 1 minus x squared. When we integrate x with respect to y, we get x times y from y equals 0 to y equals 2 minus z. And then we're going to integrate with respect to z, and lastly with respect to x. So we have negative 1 to 1, 0 to 1 minus x squared, x parentheses 2 minus z minus 0, dz dx. Negative 1 to 1, 0 to 1 minus x squared. So when we distribute, we get 2x minus xz, and we're going to integrate with respect to z and then with respect to x. So now we can integrate with respect to z. So we have negative 1 to 1 for these bounds. Let's go ahead and integrate. When we integrate 2x, we get 2xz minus, this will give us 1 half z squared, so 1 half xz squared, from z equals 0 to z equals 1 minus x squared. Then we're going to integrate with respect to x. So we have negative 1 to 1. So we have 2x parentheses 1 minus x squared. Let's put a bracket here. Minus 1 half x times 1 minus x squared, quantity squared. So the integral from negative 1 to 1, here we have 2x minus 2x to the third minus 1 half x times 1 minus 2x squared plus x to the fourth when we do FOIL here, dx. So negative 1 to 1, we have 2x minus 2x to the third minus 1 half x plus half of 2 is 1, and that makes x to the third, minus 1 half x to the fifth with respect to x. We have like terms on the 2's and the x to the third, so let's go ahead and combine those. So we're going to integrate from negative 1 to 1, and 2x minus 1 half x is 3 halves x, and negative 2x to the third plus x to the third is minus x to the third, minus 1/5 x to the fifth, and we're going to integrate with respect to x. So we have negative 1 to 1. Oh, we don't need to write our integral because we're going to actually integrate this time. So when we integrate 3 halves, we get 3 over 2 times 2 is 4x squared, minus 1/4 x to the fourth, minus 1 over 5 times 6 makes 30, x to the sixth. And the bounds are negative 1 to 1. Now some people here put from, you got to check symmetry, but it's all even. So since we have y-axis symmetry, we can see that in the graph as well. You could double it and go from 0 to 1, but I just always work with it as it is. So we have 3/4, and when we put in 1, we get all of these values. And since they are all even, then we get the same thing in this next parentheses, which is 3/4 minus 1/4 minus 1/30. Notice they match, so the value of this triple integral is 0. Interesting answer. Correct and interesting answer. All right, so let's look at the next concept. Changing the order of integration. Fubini's theorem for triple integrals lets us write our integral as an iterated integral, and there are 6 different ways which we can do it. So when we look at this problem, Let's start off with the fact that this is defined to be a triple integral, where you have some function in here. And when you actually put bounds in it, let's say a to b, c to d, and I forget what letters we use here, s to t maybe, of f of x, y, z, d, v. This is called a triple integral because it's a triple integral. And this one is called the iterated integral, where you write them out into very specific values. So our goal is to learn to change the order of integration. Let's look at a very specific example. It says express the iterated integral, the integral from 0 to 1, the integral from 0 to x squared, and the integral from 0 to y, f of x, y, z, dz, dy, dx, as a triple integral, and then rewrite it in the following order. So first of all, we need a triple integral, so that's not bad. That's what we see up above. And then part B, we're supposed to integrate first with respect to x. So integrate first with x with respect to x. Then z, then y. And lastly, we're supposed to integrate first with respect to y, then x, then z. By the way, these are dittos. Hopefully you know what it means. It's copy and paste before there were computers. So it keeps me from having to write it all again. So we have that triple integral. When we write it, part A, when we write it as a triple integral, we say over the region of f of x, y, z of dv. Now, in order to change our order of integration, we need to actually look at what these bounds are. So let's draw an xyz plane. And let's look at what we're given up here. Our x values go from 0 to 1. So that's pretty nice and easy. Now our y values go from 0 to x squared. So that means we have a parabola happening in here. So think about the fact that, let's label x, y, z before I go any further. And so we have a parabola coming like this. This would be easier for me on a 2D plane, but we're going to kind of draw it here. And then dz goes from 0 to y. So dz goes from 0 to y in the dz plane. I cannot put this in 3D, so what I'm going to do is I'm going to map it on to the different planes, but I'm going to show you a picture of it first. So this is what our figure looks like. But before we continue on, in order to change our order of integration, we need to think about what is happening at the planes. So let's talk about these bounds. And let's start with 0 to 1 for x. Let's talk about the xy plane. So here we have the xy plane. And as we look at the xy plane, the x goes from 0 to 1, and y goes from 0 to x squared. So this is what we have here. And in this case, x goes from 0 to 1, and y goes from 0 to x squared. So now let's look at the yz plane. So here's y, and here's z. So y goes from 0 to 1, and z goes from 0 to y. So this is technically the line z equals y. So you can see it's happening like that. So this is 0 to y. And then we're going to do the last set, which is the xz plane. And since z equals y, then it's going to match the other one. So x goes from 0 to 1, and z goes from 0 to x squared. So you can see how we have these set up now. Now we can start to build our triple integral, our iterated integral. I call them all triple integrals, but you should probably keep them separate a little bit better. So let's start with the fact that part B, says we're going to integrate first with respect to x, then z, then y. So we're going to build this all in terms of y because y comes last. So let's say E equals the point x, y, z, and it doesn't matter which order you build this here, because if you build your domain set or your area of your region on the planes, then it'll be easier to build your integrals. So let's start with y, because y is the easy one. Let's start with this one up here, the purple star. And y is going to go from 0 to 1. So y goes from 0 to 1. And then we can build x. X goes from this curve to 1. Now, since y equals x squared, this means x is the square root of y. So we're going to say x is between the square root of y and 1. And then thirdly, we need to put it in terms of z. But we're taking y to z. So let's look at the graph on the yz plane, which is the one with two purple stars. And we're going to integrate z and then y. So y is going to be 0 to 1. And then z is going to be 0 to y. So z is between 0 and y. Hopefully that makes sense, but that's how we have to write it. So then we're going to write our iterated integral, not our triple integral. And they didn't give us a function. They just said the function of x, y, z. So we're changing variables. Now if you look at the directions, we're integrating first with respect to x. So the x bounds, if we move up here, are from the square root of y to 1. Then we're integrating with respect to z. And the bounds for z are 0 to y. And then lastly, we're integrating with respect to y, and the bounds are 0 to 1. So hopefully that makes sense, and that's what we had to find for part B. So now we're going to do part C, and it says to integrate first with respect to y, then x, then z. So let's build our E again, because when you can build what your region looks like, you can do a whole lot better at building your integral. Now we're integrating last with respect to z, so we want to put everything in terms of z. And let's start with the YZ graph over here. And I put one blue star. Now we want to end up with z, so z is going to be 0 to 1. So z is between 0 and 1. Whatever you integrate with last has to have solid boundaries, constant boundaries. And that's because when you have a definite integral, you have to end with a constant. You can't be adding a variable in at the last minute. So now let's look at y. Now there's a problem with y. Y is happening here and here. So y is in two different graphs. So notice over here that y equals x squared, and over here y equals z. So the two boundaries for y are going to be x squared and z. So if we look at this 3D graph, we have x squared as your right boundary and z as your left boundary. So y is between z and x squared. And then lastly, we're going to look at x. And as we look at x, we're going to look at this graph, this far graph over here with two stars, two blue stars. So we already know that z is 0 to 1. So let's talk about this. Z equals x squared, so x is equal to the square root of z. So when you look at this, x is going to be between the square root of z and 1. So x is between the square root of z and 1. So we can build our iterated integral of f of x, y, z. Make sure you do it in the right order. First with respect to y. So y is going to be from z to x squared. And that makes sense because it has to go first in this case because we have all these variables happening. And then with respect to x, so dx is going to be from the square root of z to 1. And lastly, with respect to z, and the bounds will be from 0 to 1. So that is your iterated integral for part C. So doing this isn't bad. You just have to draw out all of your regions so that you can see how they fit together to make it happen. All right, so moving on. Applications of triple integrals. I did warn you that this section is all, everything we did with double integrals pushed into triple integrals. So here we go. Everything that we did with double integrals we're doing now. So it says use a triple integral. This says use a triple integral to find the volume of the tetrahedron T bounded by the planes x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So I don't mind that you look at the graph of a 3D figure on Desmos. I will give you the graph of the 3D figure, but you have to be able to build the graph of the 2D region. So when we did this earlier in chapter 15, like 15.2, area over general region, you can do it with a double integral, but this is showing you how to do the same thing with a triple integral or an iterated integral. So let's start with the 3D figure. So when we look at this figure in 2D, we're going to look at it in the xy plane. So here's my xy. And we're going to take this equation and say x plus 2y equals 2. So my x-intercept is 2, and my y-intercept is 1. So then we could say that y equals negative 1/2 x plus 1. Either way, x plus 2y equals 2, one of the two. So we have this equation here. Let's look at the next equation. It says x equals 2y. So let's call this y equals 1/2 x. It starts at 0, goes up 1 and over 1. So this is y equals 1/2 x, or x equals 2y. It's the same line. And then we also have the plane x equals 0 down here. X equals 0. And lastly, we have the plane z equals 0, which is what gave us our equations. So we are good to go. And we need to build our triple integral. So we're going to say the triple integral over the region E. And if you look at the tetrahedron, the lower boundary of our tetrahedron is the plane z equals 0. And the upper boundary is this equation. But we don't have an equation in terms of x, y, and z. Those are both boundaries. So keep in mind the words boundaries are important here. So we're going to find the triple integral over not E but T. It's the tetrahedron T. And we have in terms of the volume. I think it's easiest to write out your boundaries. So let's start with T equals set of points x, y, z such that, and let's do x last because x is involved with everything. So let's talk about x goes from 0 to 1. It's a definite for us there. So x is between 0 and 1. And then let's talk about y. So y goes from the blue line to the pink line. So that means it goes from 1/2 x up to the pink line, which is negative 1/2 x plus 1. And then we're going to look at z. And z is bounded at 0 right here. And then it goes to the second equation, which is 2 minus x minus 2y. So that gives us our bounds in that area. Let's start with z because it has two variables in it. So as we write our triple integral, our iterated integral, I'm going to do x last from 0 to 1. I'm going to do y next to last, so we have 1/2 x to negative 1/2 x plus 1. Notice there's only x's there, so it should go second. And our z goes from 0 to 2 minus x minus 2y. And then we have dz, dy, dx. It's the understood one that we integrate. So we're going to bring these two down. And I'm going to go ahead and integrate when I finish writing. I'm going to integrate with respect to z and get z from z equals 0 to z equals 2 minus x minus 2y. And then we're going to integrate with respect to y and with respect to x. So we're going to keep these integrals here for a minute. One of them for a minute, the other one's going to last longer. It just is that way. And we get, in place of z, we get 2 minus x minus 2y minus 0, which we're going to leave off, and then we are going to integrate with respect to x and with respect to y. So let's start with respect to y. So we get 2y minus xy minus 2y squared over 2, which is just y squared, from y equals 1/2 x to y equals negative 1/2 x plus 1. And when we're finished, we're going to integrate with respect to x. So we have the integral from 0 to 1, and we have 2 times y, which I'm going to use a bracket here. So we're going to evaluate, we're going to say 2 times y, which is negative 1/2 x plus 1, minus x times that gives me x times negative 1/2 x plus 1, minus negative 1/2 x plus 1 quantity squared, minus, when we evaluate at y equals 1/2 x, we get 2 times 1/2 x is x, minus x times 1/2 x is 1/2 x squared, minus y squared would mean we take 1/2 x times 1/2 x to be 1/4 x squared with respect to x is our last integration. So we're going to go from 0 to 1. We have 2 times negative 1/2 x is negative 1x plus 2, minus, distribute that next, the x, it becomes plus 1/2 x squared minus x minus parentheses 1/2 x times 1/2 x makes 1/4 x squared, minus 1/2 x minus 1/2 x makes minus x plus 1, and then we have minus x plus 1/2 x squared plus 1/4 x to the 4th, and then we're going to integrate with respect to x. So let's distribute one more time. Negative x plus 2 plus 1/2 x squared minus x minus 1/4 x squared plus x minus 1 minus x plus 1/2 x squared plus 1/4 x squared with respect to x. Now, if we look carefully, these 1/4 x squareds cancel beautifully. I have several negative x's, but I don't think anything else cancels. So now let's continue on. We have the integral from 0 to 1. Let's start with x squared. I have a half and a half makes a whole. So we have x squared minus x, and these cancel. So we have minus 2x, and then we have plus 2, minus 1 makes a plus 1, and we're integrating with respect to x. So when we integrate that, we get 1/3 x to the 3rd minus 2 over 2 is 1x squared plus x from 0 to 1. So this means we have 1/3 minus 1 plus 1, which equals 1/3, minus 0 minus 0 minus 0. So it's not too difficult. Notice the 1/3 for the answer. The hardest part is building this set of boundaries, because if you can build the set of boundaries, then it all makes sense. The next part is moments and center of mass. So think about moments. When we worked in double integrals, we would say if we were going about the x-axis, we would have the double integral over the region D of y times rho of xy with respect to the area. And if we're going about the y-axis, we would have the double integral over the region D of x times rho of xy with respect to the area. So now we're going to pull this into triple integrals, and we're going to say that the moment, and we're going about the 3 coordinate planes. So the moment in terms of the YZ plane is written as the triple integral over E, and we have x times rho of xyz with respect to the volume. And the moments about the xz, I guess we'll do xz next plane, is the triple integral over the region E of y times rho of xyz. Again, I won't make you memorize these. And the moments about the xy plane is the triple integral over E of Z times the rho of XYZ in terms of the volume. In terms of the volume. So then your center of mass, we did the center of mass. There's two ways to do it, and I chose the way that I felt like was the easiest formula to give you. So we did x bar equals 1 over m times the double integral of x times rho of xy in terms of the area. And the y coordinate for the center of mass is 1 over m, and you had y times rho of xy in terms of the area. And remember that m is the mass, and the mass is given as the double integral over the region of rho of xy dA. Now, back in that lesson, I always worked it out this way because I went ahead and found it to just be easier to do it. You could have said over here, let me find a different color. You could have said that x bar is equal to m of y over little m. I just find that when I use these two formulas, I mix them up. So the moment about the x-axis and divide it by m. So I like the pink ones better. I'm less likely to mix them up because here I have in the y one I have a y bar and I have a y. So that's why a couple of you have asked me which way I prefer to do it. I prefer to do it according to the pink formulas because that works in my life, but you can do it the other way if you'd like. Now when we talk about the center of mass here, we're going to say that they're going to use this formula. They're going to say x bar is equal to the moments above. So x bar is equal to the moment of yz over m. Again, I wouldn't use that formula. I would say 1 over m times the triple integral over e of x times rho of xyz with respect to the volume. So if it were me, I would keep it consistent as long as you're consistent in what you do. They're going to say that the moment in terms of y is xz over m. So we're going to say 1 over m times the triple integral over e of y times rho of xyz with respect to the volume. So then you can tell that z is equal to the moment of xy over m, which is 1 over m times the triple integral over e of z times rho of xyz with respect to the volume. My z is falling apart right there. With respect to the volume. And remember that your m is equal to, like up above, I'm going to put it up here. So m is equal to the triple integral of rho of xyz with respect to the volume. So the formulas are very similar, very parallel. And since we've done a lot of triple integrals already, I think as long as I help you set it up, you're good. We will look at an example, probably. Now, the next one we have is the moments of inertia. Before we continue on, if the density is constant, the center of mass is called the centroid of E. And I don't know that you need to find that anywhere, but the centroid is the center of mass. The center of mass if the density is constant. I'm not going to ask you for that. Might the word centroid pop up in your homework? Possibly. I mean, in your exercises? Possibly. So that's why we went ahead and talked about it. All right, next we have the moments of inertia. So let's talk about the moments of inertia. And I had that right here. So the moments of inertia that we had before, remember I'm giving you these formulas, so I'm going to give them to you in the form in which I put them in the video. So if you're watching the video and working it out with me, life is good. I might give you both forms. We'll see. So the moment of inertia is I sub x. The moment of inertia about the x-axis is the double integral over d of y squared times rho of xy with respect to the area. The moment of inertia about the y-axis is equal to the double integral over the region of x squared times rho of xy in terms of the area. So you can imagine that if we're going to put this into, and then the moment of inertia about the origin, let me not leave that one off. So the moment of inertia about the origin is equal to the sum of those two moments of inertia. Okay, so let's move this into our triple integrals. And when we do this, we find that the moment of inertia about the x-axis is equal to the triple integral over e. And we have y squared plus z squared times rho of xyz with respect to the volume. And the moment of inertia with respect to y is going to be x squared plus z squared. You can see how these formulas are all very similar. That's because the rules of math don't change. We just step it up and add it to it. The moment of inertia for z is accordingly, and it's x squared plus y squared times rho of xyz with respect to the volume. And that pretty much handles that. We don't have the moment of inertia about the origin on this one. And next we're going to do the electric charge. And so when we're finding the electric charge, we say that Q is equal to the triple integral of sigma of xyz with respect to the volume. And that's very similar to the one that is for double integrals as well. So I'm not going to write that down, and we're going to move on with it. Let's go back up here. Remember that this rho is your density constant, your density. So this is your density function happening here. So if your density is constant, then when you find the center of mass, that's the centroid. So that comes in that aspect. Okay. I think that'll give you everything you need to have to complete this lesson. And I hope that you enjoy it. Triple integrals are kind of fun, and I hope that you find them to be such. Have a great day.